Good evening, everybody. I can't see any of you, but it's a real pleasure to welcome you here this evening for this very special event. So I'm Colin Darkin, I'm the head of the engineering department, and we're here to hear from Alex Kendall. I'll say a bit about Alex in a few minutes. One of the reasons why we wanted to do this is because we've just entered the 150th anniversary of this department, so this academic year. So it was founded back in 1875 with the establishment of a professorship of mechanisms and applied mechanics, because there was a lot of interest in trying to understand how machines behave. And there were all sorts of machines, of course, at the time: electric motors, in the internal combustion engine that was invented a few decades previously, and of course the old-fashioned steam engine. And an interesting thing is, at that time, not many people realize this, but at that time, electric vehicles were dominant. They were outselling internal combustion engine cars by a rate of 2 to 1. And people weren't that interested in internal combustion engine cars, despite their power, because there wasn't the infrastructure for refueling. And I know, and here we are, 150 years later, saying the same thing about electricity. But just down the road, a few years after that, of course, the electron was discovered. I always think that's an odd phrase because it makes it sound like somebody lost it in the first place. But it was discovered by our colleagues in the Cavendish back in 1897. That led to the whole field of electron physics, which then evolved into electrical and electronic engineering. This department has been deeply involved in all of these developments, from the internal combustion engine, which doesn't have to be a bad word, to the invention of the jet engine. We've put a lot of effort into reducing the emissions, both chemical and noise emissions from aircraft, helping to try to achieve net zero aviation. There's all of the work on electrical systems. So the electrical engineering led to the electron microscope, which then led to, and this is from this department, the invention of electron beam lithography, which is a technique adopted by the semiconductor industry to create microprocessors. And that's why we are able to continually miniaturize transistors in our microprocessors, and that's what enables us to do things like machine learning. And run the complex code that we do, that we all rely on in our daily lives, from everything from our wearable watches to our phones to our drivable cars, or self-driving cars even, and our computer systems. And we are entirely reliant on these. And the engineering department has played an enormous role in, from the early stages of artificial intelligence, machine learning. It's been a real hot pot of invention. And here we are coming full circle now, putting all of these components together in what will one day soon, well, already actually, self-driving electric vehicles. And so I'm not going to bore you anymore, but just one quick thing before I introduce Alex. You can probably see there is a fire exit to your left, and there are two up at the top at the back of the room. And there aren't any planned fire alarms or fire drills. So, Alex came to us 10 years ago as a fresh-faced PhD student, wanting to work on something to do with control or machine learning. He was very passionate about wanting to do something that would create impact, and my goodness, and what a journey it's been. And I'll let Alex tell us what the journey is, what it was. But he completed his PhD in 2017 and then went on to create this company, Wayve, which is one of the major players in the automotive industry. It's doing really transformative work, sort of moving towards embodied AI and self-driving. And there is so much more behind it that Alex will tell us about. I'm really delighted that Alex agreed to come today, because I think there are so many people that will be inspired by this story, that a student can come, and with the right backing. He worked with Roberto Cipolla, who's here, and was a key member of Division F during his time here, and has sort of gone out into the world gone on this amazing journey. And Wayve has won all sorts of prizes. It's raised over £1 billion in funding. And I think this is clearly just the beginning. And Alex, would you like to come and join me on the stage? And tell us about your journey.
Wow, it's amazing to be back here. I had the chance to spend the afternoon here. I'm really excited to talk to you about frontiers. We've just been hearing about a number of frontiers that have happened here at the engineering department as we celebrate the 150th birthday. But I'm really excited to talk about the frontier of embodied AI. And today I'm going to talk about three things. Firstly, a bit about embodied AI, what it is and where that frontier is today. Secondly, talk about my own journey and what it's been like developing and growing this technology to where it is today. And then third, a bit about where we might be looking next. But I want to start off with and talk about what we mean by embodied AI. And like all good stories, I'm going to start off with some motivation from science fiction. Embodied AI is all about bringing AI into the physical world. And of course, we've heard about all of the impact that AI is having today in software. But what happens when you give it a physical interface to the world? And we've seen many examples of that in science fiction, of course, whether it's KIT, the talking car, or C-3PO from Star Wars. Physical machines that we can trust to enhance our lives and interact with us. This is the promise of embodied AI. Now, first and foremost, I think embodied AI is fundamentally the next generation, the next wave, no pun intended, the next wave of tools. And tools is what has set apart the human race from other species on this planet. If you think about the formative tools we've seen from other animals in the kingdom, whether they're simple sticks or spears or things like this, the incredible technology that we've been able to build as a human race is really what enables us to live such a prosperous life. And fundamentally, embodied AI is going to be just a complete step change and next step in this journey. If you think about the very first wheels that we were able to put together, or the calculator and what that's done to fields like accounting, or X-ray machines for medicine, or now self-driving cars, what we're going to talk a lot about today. I think fundamentally these tools really allow people in all kinds of different occupations to do so much more and to achieve more. And I think embodied AI is just going to be a complete step up with this. Tools that are not only give us leverage, but that are intelligent. Tools that allow us to actually trust and delegate tasks to. Now, before we dive in, I think it's important to talk about, of course, there are perhaps many risks and challenges with creating this future, but I think there are going to be fundamentally some really key things that can underpin this vision, this promise of what embodied AI can do for us. And for me, they're these four things: intelligence, trust, simplicity, and scale. So I'd like to start off by talking a bit about these up front. Of course, intelligence, I think, is the obvious one. These tools need to be smart. They need to add value and give us utility with whatever we're trying to do. That's fundamentally important. But I think the other three are equally interesting and perhaps not spoken about as enough. Trust, of course. For me, trust is about setting the right expectations. Whether this is around safety or privacy or even being reliable and meeting the expectations. If you have a system that you know the boundaries of what it can and can't do and you can trust it, I think that's going to be so critical to seeing this technology adopted broadly. Simplicity is another interesting one. If adopting these tools requires billions or trillions of dollars of say, capital expenditure, or changing the way we live, the infrastructure we live in, or the ways we work, I think there's going to be a lot of friction to adopting it. So simplicity of use, I think, is going to be really key. How can this technology seamlessly work with society? And moreover, I think this technology needs to have an accessible interface. And there's nothing better than perhaps human language. Avoiding needing, say, a PhD in robotics to learn to interact with robots, but how can we make these things generally accessible? And I think language may be a way to do that, but ultimately the simplicity and ease of use is what's going to really lead us to this promise of embodied AI. And then finally, scale. It's not just about having these systems that are generalizable and sustainable, but importantly affordable. I'm interested in seeing a future where embodied AI can be not just a system that's operated in affluent areas, perhaps like Silicon Valley, but a system that could be truly ubiquitous. And we think about massive technology trends recently that have done that, like personal computers or smartphones. I think getting to that level of scale really does need a sense of affordability, as well as a system that can deal with the diversity around the world, whether it's the different cultures it may need to operate in, and I think that's going to be achieved by scale. So this is the promise. This is the promise, the opportunity ahead of us. Before we dive into how the progress towards building this, I'd like to take a step back and think about AI in general, and actually talk about what are the differences between cognitive and embodied AI. So when I say cognitive AI, I mean a lot of the AI that we're seeing talked about today. These are things like large language models, an AI that's being used for search engines, knowledge retrieval, or reasoning tasks that you might see through systems today like Gemini, Claude, or ChatGPT. And there's a lot of similarities between cognitive and embodied AI, but there are also a lot of differences. And I think that while a lot of where we are today has grown in a similar vein, some of the differences present unique challenges and also opportunities that I think are going to lead to different results and perhaps more important results in areas particularly like safety and efficiency. But I've put some comparisons up here and to maybe comment on a few of them. It's interesting to look at the data that's behind training these systems. We've seen recently in cognitive AI that this data is somewhat starting to saturate for pre-training. So these models typically go through both pre-training and post-training sessions, and pre-training is all about giving the base, the general purpose knowledge about the task. And we're seeing increasing multimodal models that can be trained on different forms of data, from text to audio to video, and of course action with robotics and embodied AI. But of course, in cognitive AI, this data is freely and widely available on the internet, but that's somewhat starting to saturate with us. We've now, we're reading all the data there is on the internet, and incremental amounts that are being added aren't adding significant new diversity or information. So one opportunity that embodied AI presents is an enormous open-ended sense of data. The size of data in the natural world is diverse. There's a very long tail of different situations, but the other challenge that comes with it is it's also very low signal-to-noise ratio. If you think about driving, most of it is perhaps boring, monotonous, and very rarely do you see interesting scenarios or even an image of the world. And a lot of it's not that important for driving, whether it's the sky or trees or the road behind you. And so the information content in embodied AI can often have low signal-to-noise ratio. But of course, the size of it is enormous. It's petabytes or even exabytes compared to the perhaps single terabytes that we see cognitive AI being trained on. The other interesting differences are around inference and safety. When it comes to actually running these systems, having a embodied AI system, it needs to run on an edge device, on a car. And cars are power constrained, they're compute constrained. And so that really pushes and challenges us to push the boundaries of efficiency and how much intelligence can you put into a flop of operation. And not only around inference, but also safety. It's interesting that cognitive AI is somewhat of the Wild West right now. We've got a lot of emerging regulation. It's hard to say whether that'll be over or under regulation, but I'm sure there's going to be some whiplash in how that evolves in the coming decade. We've got different companies forming different standards, whereas in driving, we have some quite mature regulation. There's clear road rules, and of course, such a core focus on safety. So I think that presents an opportunity. We're challenged in embodied AI, but also are required to really ensure these systems are safe by design. And I think that this is leading to some interesting innovation that may provide a way to unlock introspection and true AI safety. There's a real opportunity there. And of course, the corollary to safety is evaluation, and evaluation around measuring these systems, understanding them. In the cognitive AI space, a lot of this is now becoming done through red teaming and manual human labeling and creating tests that test the large suite of different tasks you want to look at. When it comes to general purpose systems, there's not going to be one test that just solves them all. It's going to be a suite of so many different tests. It's like setting the whole diversity of challenges and tests that you might see when we grow up. And I think a broad range of tests is going to be required for general purpose systems. But the interesting thing in embodied AI is, again, we can leverage the richness in the real world and actually form data-driven tests through simulation. And I'm going to talk more about that later in this talk today. So a lot of similarities. A lot of growing these systems to where they are today requires extreme engineering, systems, data, compute, scale. But I think the differences really start to pull apart when it comes to particularly safety and efficiency, which are interesting opportunities to look at. A natural next question that might be interesting to look at is, do we need embodiment for AGI? If the ultimate goal here is to build this compelling system that can really benefit society in a broad way, if we take a definition of AGI, like what OpenAI has proposed at the top here, about having highly autonomous systems that outperform humans at the most economically valuable work, an interesting question is embodiment actually needed? Or can we simply have a cognitive system that just observes the world, looks at all of the data on the internet, and becomes eminently intelligent? Well, there are a few different ways you could look at this question, and I've put some arguments here. I mean, ultimately, it does come down to a definition of what AGI is. But, I mean, if we take this definition, I mean, the first thing to point out is that most of the economically valuable work is done through physical interaction. We live in a physical world. And so if we're going to build tools that are really going to support and accelerate our work in these spaces, by definition, we're going to need to interact in the physical world. The other interesting thing is that, and this might be more of a function of the way these systems are trained today, and may not always be true, but at least systems today that are purely trained on text, we've not been able to yet see emergent spatial properties like spatial understanding, reasoning, and navigation that are critical for navigation. And I posit that if we do train these systems on navigating and interacting in the world, of course this phenomena will emerge. But this has not yet come within large language models. And what I was talking about previously, that if scaling laws continue to hold, if we continue to see these AI models just continue to get better logarithmically with more data and compute, we are starting to saturate that data, and to be able to push the boundaries and continue to make these systems more intelligent, it's likely that we're going to need to tap into the enormous amount of data that we have in the embodied space, in the real world. Now, another way to look at this might be from a neuroscientist view. Actually, here in the department, Daniel Wolpert's view was that we have a brain for one reason and one reason only. That's to produce adaptable and complex movements. And we can see this throughout the animal kingdom, that when movement and interaction is not required, intelligence disappears. And of course, the ultimate goal of intelligence is to make decisions in the world and interact. And it's interesting to look at studies that have looked at, say, animal or human development over time, and what happens if someone is deprived of, perhaps they can only observe the world but they can't interact, or if you can only listen and hear the world but not actually speak and converse. And one of the quite clear conclusions that's come out of this body of work is that interaction and the ability to actually converse and get feedback and explore with curiosity is a really critical part of cognitive development. And this has been shown through a number of different studies. Now, AI may be different, but I think there is an interesting thread there that actually the power of interaction may produce a lot more efficient learning than simply just observation. So I'd argue that embodied AI is critical for AGI, and I think that we are going to see embodied AI emerge as the next frontier. It's going to be the space that really pushes forward the next generation of breakthroughs. And moreover, perhaps in 10 or 20 years' time, when you think about someone on the street, what they think about an AI system, I think what will first come to mind is that physical embodied AI that helps them, supports them in their lives, gives them time back. And I think embodied AI is going to be what we think about with the future here. I feel like I painted this vision that is exciting, is something that we can look to, but maybe it's interesting to look at where we are today on this hype cycle of journey. Of course, we've seen AI go through many hype cycles, winters, and emerge with resemblance of value. And for embodied AI, this journey, interestingly, actually started a long time ago in perhaps 1989. One of the very first self-driving systems was actually an embodied AI system. The system, Alvin, was developed at Carnegie Mellon University, and it was a neural network, a more general driving system motivated by trying to train this car to drive on the east and west coasts of the United States. Now, since that point, most of robotics ended up developing with what we might call narrow AI, a more hand-coded way that had robots operating within a set domain, where largely these applications had hand-coded rules or set maps that told these systems how to behave. But actually, it started with more of a general-purpose system. But this was a long time before, I think, the trigger point that really started this technology to take off. And in self-driving, that was really the DARPA grand challenges in the United States. These were a US military-funded set of challenges that many academic institutions started off working to build systems that could drive through complex desert and urban driving courses. And this is what led to the commercial explosion. Of course, Google acquired a lot of this technology and built out their self-driving car program. And then many other companies spurned off the back of that. And I call this the AV 1.0 wave of this technology. A technology that is a remarkable experience if you go to China or San Francisco or some other cities like that today. You can see robotaxis driving around that are truly fantastic. They have incredible safety records and provide a glimpse of the future. But the challenge with these systems is that they're quite difficult to scale. They're not yet economically viable, and they rely on a lot of infrastructure that's only been shown to be possible in some constrained environments today. So again, coming back to this vision of what's going to push the frontier of this technology, the frontier is going to be unlocked by technology that can scale to the world. And that's where I think the promise of embodied AI can unlock. And what I'd love to talk about today, what we've been working on at Wayve, a globally scalable system to embodied AI. Now, of course, driving is not the only example of embodied AI. There's also humanoid robotics that are looking to produce general solutions. And I think they're going to produce incredible outcomes for us in the future as well. But I'd argue we're more on the earlier side of this hype cycle. They're starting off in more constrained environments today with heavy reliance on infrastructure. And I think we may see a similar journey of them through traditional approaches, constrained approaches to before they end up finding a path to scale. But another interesting question to ask is, why do we think driving is going to be that first example of embodied AI that is generally accessible? Well, on this one, I think I'm going to offer a couple of compelling reasons and why, given I've been inspired by embodied AI, why I've been focusing on autonomous driving as a first application. So these six reasons, let's talk through them. The first one is that autonomous driving is going to bring incredible benefits to society, and I think this brings a real sense of urgency and a sense of imperative to bring this out to the world. And if you think about, sadly, 4,000 people every day lose their lives on the roads around the world. 99.6% or greater of those deaths are unfortunately caused by human error. So autonomous driving gives us an opportunity to drive those accidents down to near or zero. And beyond safety, there's also benefits of autonomy, whether it's actually in the UK and the US, 1.5% of these countries' GDPs is lost to road accidents, whether it's the impact on the healthcare system, congestion, or even just the sheer time and resource delays that accidents end up taking. Or if you think about in a city like London, car parking takes up 10 times the size of Hyde Park. And the opportunity is that self-driving can bring vehicles, today they're utilized about 3% of the time on average, can bring them up to perhaps 60, 70, 80, 90% utilization, improve the sustainability of these. Even things like speed bumps cause energy wastage due to trying to enforce conservative speed through high-density locations. Opportunity to remove those, and I think fundamentally also accelerate the electrification of the world. As this technology comes in, it can also cultivate and be coupled with the choice to electrify fleets. There's loads of really beneficial outcomes when we get this technology right. But then there's also some other key reasons, like availability of data at scale. There's tens of millions of cars at the moment driving around the world that collect imagery and data that we can train these systems on. That's fundamentally critical for making this technology possible. Another key thing is that we can see benefit from driver assistance, from a partial autonomy use case. So we don't need to wait for full autonomy, but we can take society along the journey of going from partial to full autonomy and start to realize value sooner and learn and iterate rather than having to wait for some big bang of full autonomy like you might need in a domestic or manufacturing robotics setting. There is a global install base, the fourth reason. Not only are there cars around the world with a supply chain that's mature and robust, with computers in these cars and sensors that are sufficient to run this technology, but this is at global scale, which means that we don't have a heavy capital expenditure, manufacturing and supply chain job to be able to bring this technology to market. I think that's a huge accelerant. And then finally, the business case is beyond compelling. It's an incredible one that allows us to attract the funding to actually go and build this quickly. So these reasons are why we'll see it in self-driving first, but of course, this is just the tip of the iceberg. And embodied AI is going to be able to bring benefits to a number of different sectors beyond transportation. All right, so let's take a step back beyond the vision of embodied AI, and I'd love to talk through the journey that I've had in my life and some of the work that we've been doing at Wayve. So I'd love to talk about the frontiers that that have driven me and that I've been exposed to. And really, they started back home, growing up in New Zealand, where I had the chance to chase frontiers, whether that's been in sports teams or climbing mountains. And I think the values that I really took from those formative experiences were ones of adventure, grit, curiosity, and I think they've become so important in many engineering pursuits in my life. But actually, one of the most exciting engineering projects I got to work on at the end of high school was developing a drone. And this was, for me, one of the first experiences that opened me up into how important cross-functional and different areas of technology was so interesting to bring together. A drone is an example of mechanical and 3D printing, electrical and software to build the Kalman filters to make it stable. And bringing that together, and yes, I did use it to chase some of the sheep around our property, but bringing that together was just such a fantastic experience. And one of the things that was so exciting to see was that many years later, I got the chance to go to Silicon Valley and be part of this incredible startup, exposed me to entrepreneurship, and had a very small part to play in building this consumer product. A drone that's on the shelves now that you can buy that can fly and autonomously dodge trees and film you while you're skiing or mountain biking or doing a creative pursuit. And actually, the very first photo on the slide on the top of the mountain in New Zealand was taken by this drone. But I was really fortunate enough to receive this amazing scholarship that brought me over to Cambridge. I'd never been to Europe before, and stepping foot in Trinity for on my first day where this photo was taken was the start of just an incredible adventure that exposed me to so many frontiers. And I think the really special thing about being here at Cambridge was how many different diverse sets of frontiers of research that I was exposed to, and just some incredible minds. And I loved the period of time that I spent here. One of the first things that we were able to put together was a system called SegNet. And I was, again, going back to this theme of bringing together different disciplines. I was fascinated about robotics and building intelligent machines because I think it's one of the most incredible frontiers to work on. And I didn't have a large background in more traditional robotics. And so Vijay, who's here, was the very first person at Cambridge who was starting to work on deep learning. And bringing these ideas together with deep learning and applied to computer vision and robotics was just led to a wealth of interesting research questions. And this was one of the first instances we put together that was able to tackle the problem of semantic segmentation, working out what's around you and what a robot can see. And we applied end-to-end deep learning to so many different problems. Roberto, Vijay, and many others of us in the lab, whether it was segmentation, depth estimation, stereo vision, localization, figuring out where we are, what's going to happen next, uncertainty estimation, all of these different problems. And by the end of my PhD, we were able to produce systems that could really understand a scene quite well, whether it's understanding the geometry, the semantics, or the motion. And I think this really gave me the confidence to say, look, we can build intelligent machines that can see the world around them for themselves, make their own decisions, and understand the complexities of the real world. And at a similar time, I was so inspired by what we were seeing the team at DeepMind doing, being able to develop intelligent agents that could learn at vast scale within simulation. Now, this was at very low dimensional state spaces, but at enormous scales of data, and the control and the systems that these were learning were amazing. So perhaps bringing these systems together and, again, recombining ideas, I think where the world was going was learning systems that could produce behaviors that are more complex than what we can hand engineer. And that vision that was very contrarian to the rest of the industry, the autonomous vehicle industry almost entirely rejected this idea at the time, saw it as unsafe, crazy, it would never work. But I guess this determination and belief is what led to starting Wayve. We started around the corner in a house and built our first prototype, which you can see here in the garage. But what a journey it has been of many, many frontiers since then. Ultimately, we set up Wayve to address this problem of building intelligent machines that we could trust, starting with autonomous driving, but the exact same vision that I've been talking about, this vision of creating a system that can truly scale, that can be cost effective, not rely on the infrastructure or LiDAR, laser scanners that other autonomous vehicles required, but have something that can scale and do so with the power of end-to-end deep learning, the power of embodied AI. And I'd love to show some videos of this system learning throughout the years, from some of the very first steps it took in Cambridge through to where we are today. And on the left is a video of, this is actually me in the driver's seat, and of our first prototype learning to lane follow. This was actually at the Cambridge Polo Club, so you might see some horses in the field on the right. But the system was trained with reinforcement learning, and the reward was asking it to drive as far as it can without any human intervention. And every time there's a human intervention, it learns from that and learns to try and drive further. And you'll see after a few pieces of feedback, it'll start to learn to correct and wobble down the road. And after 10 examples of feedback, it actually learns to lane follow. Now, this is very basic, very simple, very constrained environment, but was a really exciting place to start because it was the first time a reinforcement learning system had actually been put on a physical robot with visual input. And seeing it drive a car in the real world was a really exciting frontier and breakthrough of a frontier for us. Of course, we then had to scale it up, and this took us from online reinforcement learning to offline offline policy learning, where we started to train on large amounts of data, and over the next few years, improved the system so that it could drive in many diverse environments. We started driving in Cambridge, moving to London, all of the complex jaywalkers, cyclists, snow, roadworks, everything that you get in these kind of environments. And it's just been learning and growing emergent behaviors over time. And one of the things that was really exciting for us about a month ago is we just launched a fleet in the United States. And so the latest thing that our embodied AI has learned to do is now drive in the US. And you can see in this video on the right, we're driving in San Francisco. The US presents many interesting new challenges for driving, but if I maybe move forward in this video, you can see here, we go through some fairly heavy traffic, or even come through a tunnel. And one of the most interesting things for me in this expanded learning and generalization of the system is seeing how it generalizes to new cultures and new environments. Another, I guess, form of a frontier. And in this video, you're going to see us drive through a four-way stop sign and take a right at a red light. These are driving cultures that you see in the US that you don't see here. Now, the exciting thing for me in this is an example of very efficient generalization. Our embodied AI has had 5+ years of learning to drive in the UK. It's learned how to drive really robustly in London in an urban environment. We launched our fleet in the south of San Francisco Bay, where it's mostly suburban and highway environments, and it had a couple of weeks of experience in this environment down there. This video is from the very first day we took the system to San Francisco. It had never been to San Francisco before, had no training data from there, no high-definition map that was telling it how to drive. And here you can see it was able to show not only could it take the urban driving experience from London and from South San Francisco Bay, the US driving culture, but bring these together and generalize to a new environment like San Francisco, and show it could bring those together to drive in an urban setting with US culture like right turn red and four-way stop signs. That's pretty cool. That's a system that's been able to generalize to a new environment and bring together different forms of knowledge. And this is the kind of level of intelligence that I think is going to be needed to bring this technology worldwide, to be able to deal with situations that it's never seen before. We are never going to be able to show an embodied AI system an example of everything it's going to see in the wild. Every day we have new weather, new traffic patterns, new scenarios, and this kind of intelligence is what's required to bring this technology to scale. So that's where the system has learned to and grown to where it is today. But there's a number of interesting scientific frontiers that we've tackled in order to get here. And I'd love to, I'm just finished by highlighting a few of these. On the left, Lingo. It's a system that brings together language and driving. In the middle, this is Prism, a system that allows us to re-simulate scenes with photorealistic accuracy. And on the right, these videos are not real. These are actually generated. They're a world model that's able to use generative AI to generate novel content and actually simulate interactions through it. So let's start with the last one. Gaia is a really exciting system that allows us to generate new content. And I think what generative AI is now able to do in terms of creating imagery and scenes, and not only the imagery, but the interactions in them, opens up so many opportunities for embodied AI, namely around measurement and safety, allowing us to simulate and understand how scenarios might occur, or create scenarios that might be adversarial, too rare to see in the real world, or perhaps dangerous to experience. And we can generate different weathers, different lighting conditions, or even ask a system to generate, can we be 15 meters behind a bus and be accelerating right? And you can see how the scenario plays out. These world models are hugely powerful for generating data, simulating and understanding these systems. The second one I'd like to dive into is Lingo. So Lingo is a system that brings together for the first time a vision, language, action model. We've seen cognitive models that bring together language and vision, but vision, language and action is interesting because it allows us to see the world, drive a car, as well as interact with the system with language. I think this is going to be, as I said at the start, a huge opportunity for improving the accessibility of these systems, to introspect them and understand why they do what they do, or even provide them with feedback and personalize them. But this is an architecture diagram of how the system works. We take the large-scale imagery data. These can be very, very high dimensional. If you think about the 6 to 10 cameras you have around the car that are multiple megapixels each, the radar data, and then you multiply that by the time dimension, perhaps tens of millions of numbers that we compress down and tokenize into low dimensions and combine with text and other learned representations around navigation or other things like this. And the system can all be trained end to end to understand and generate content, whether it's driving actions or language understanding. And the results are really neat. On the left, you can see an example where it's driving and actually commentating on its driving, explaining its actions. And here you can see it describing it's slowing down for a jaywalker, telling us the turn it's about to make. This provides us with an opportunity to build self-driving cars that aren't like getting in a train on invisible railway tracks, but actually like getting in a car that can be collaborative with you, one that you can talk to and maybe ask to drive in a certain way that meets your preferences, and really start to delegate tasks to this embodied AI system. Or on the right, this is us asking the system questions. We're asking the Lingo whether it knows what's on the left, or actually asking, can it see any cyclists in the scene? And if you can see in this video on the right behind some of the cars, there actually is a cyclist hidden there. And Lingo spots it and talks about it. So this is really interesting from assessing risk, assessing safety, assessing what the system understands, and provides a path for us to actually introspect these models in a way that's accessible through natural language. So let me bring this all together and say that this is a technology that's on the path towards providing an embodied AI solution that can be globally accessible and I hope is inspired to and can live up to the vision and those 4 aims that I listed at the start. Intelligence, scale, trust. And of course, to bring this system to scale, it's also important to say that we have a lot of work to do to bring this into product. But what we've been able to show today, I think, is a glimpse or an example of something that can lead to that vision. And what we're excited to be working on now at Wayve is really taking that into product and to see the system deployed at large scale through driver assistance, through an experience that can give you hands-off, eyes-on, or hands-off, eyes-off driving. So what this means is that everywhere in a consumer vehicle, you'll be able to drive with a hands-off, eyes-on experience where you monitor the system. And in some scenarios, you'll be able to be hands-off, eyes-off, where you can be reading a book on your phone, or the car will give you your time back, and the embodied AI system will take the liability for the driving. Now, the exciting thing is that the percentage of the drive that will be covered by that hands-off, eyes-off will grow over time. It will grow with data, it will grow with experience as we continue to improve the safety and trust of the system. And ultimately, when the system is capable of driving door-to-door, hands-off, eyes-off, then of course it opens up driverless applications at scale, whether that's robotaxis, delivery, or logistics. And this path is something that we're so excited to go to, and I think will then continue to lead into other applications, whether it's domestic robotics or manufacturing robotics, and really provide more broad embodied AI that can benefit all kinds of areas of our lives. And of course, to get there, from day 0, we've been focusing on scale. Whether it's today, we're now training from data from over 15 countries, or we've integrated into many different types of vehicles. You can see some of them on the left here. Or the more interesting thing for me has been every time I get in the car and perhaps see a new behavior for the first time, the emergent behaviors that have come out over time that are quite human-like. If you come in our car and drive in central London, you'll see it nudging and navigating through traffic in a way that doesn't follow lanes and rules rigidly, but drives with human expectation and perhaps the driving culture that we expect to see. And I think that's really important for trust, because if you sit behind an obstacle and wait for it to clear, you're going to cause a lot of road rage. Whereas if you can, in a safe manner, overtake a double parked vehicle or keep the traffic flowing, and that's really important for the integration into the cities that we live in. And I spoke at the start about the ease of use and making sure that we don't need an infrastructure overhaul to be able to see this technology deployed. So that's so exciting, and I really hope that everyone here will get a chance to ride in the Wayve soon. But let me finish by summing up some conclusions about perhaps what I've learned from chasing these frontiers over the last 10 years, and secondly, what's next, what's coming next. I was reflecting on some observations of chasing these frontiers, particularly coming back here today and thinking about this journey. And here's some things that I might be able to offer. The first one is that I think it's so important to chase the hard things first. Why is this? Well, by going after the hardest thing first, firstly, it puts you in the space of chasing a frontier, which results in us doing new things. It results in challenging and stimulating work. And of course, surrounds yourself with excellence. But of course, doing the hardest thing first means that you start with the end vision in mind. It means that you're skating to where the puck is going. And I think that there are so many things possible today, but the more interesting questions come in from asking what's possible in the future. So by tackling the hardest thing first, it ensures that you're not going to build something that's going to be incremental or perhaps hit glass ceilings in the future, but really enables an end vision, especially if you hold a conviction around the end vision. Secondly, we've seen time and time again that data-driven systems can outperform hand-engineered solutions. So systems that learn from data, and particularly when you can build infrastructure that's strong enough to be able to drive a self-supervised learning loop. and expose them to enormous amounts of data, these are the systems that produce the incredible outcomes that we've seen. And this applies not just to the agents, the embodied systems that we want to operate, but also to the simulation systems, the measurement systems, and all of the supporting infrastructure around it. Data-driven systems fundamentally scale and outperform hand-engineered systems in a superior manner. These frontiers that I've been chasing, I also hope that it doesn't appear just like a rocket ship that's just worked from day one. It's been 10 years of incredibly hard work, including some very late nights for a couple of years in the full-side lab upstairs here. But there have been so many setbacks along the way, many things that haven't worked. And one of the things that's been so important for our team is to have the humility to not assume that we know the solution, but having this conviction behind the why what we're doing and this intrinsic motivation, and this shared purpose has been critical to allow us to push through the complete roller coaster for today, and that I'm sure will continue from here onwards. And then finally, I talked about this a little bit throughout this conversation, but cross-discipline work is something that I just can't stress is so beneficial, is so invigorating. And embodied AI, one of the special things about it is the most cross-functional problem, from mechanical to electrical to software engineering to public policy, law, regulation, or of course all of the infrastructure that's required to make this a success. It's a complete cross-functional challenge, and it's of enormous magnitude. And bringing all of these skill sets together is inspiring and creates a huge opportunity for innovation. So there's some conclusions, but I'd love to end with an ask or a call to action, and perhaps an area that for me I called out is I think underexposed, underworked on, and we see in the field of AI that there's so many folks that are today throwing money at the problem with extraordinary levels of capital expenditure to be able to brute force scale, pursuing scaling laws. Now, an opportunity that embodied AI presents is, I think, embodied AI, we're at just the beginning of this problem space. Cognitive AI is now at the point where we're chasing commercial applications. The application layer is exploding, and finding ways to commercialize and build impact and value from this technology is where the focus is at today. We're seeing these systems perhaps start to saturate in what they can be done from pre-training from the internet, but combining them in new ways and bringing together agentic reasoning or post-training is perhaps where some of the frontiers are going next in cognitive AI. But embodied AI is a complete, I think, blue ocean opportunity. We're just getting started. And so this presents a huge opportunity, and perhaps a call to action that I can leave today is that I hope if you're interested or inspired or excited about this area, there are so many interesting problems to tackle here. And I'm going to call out two of them. Two of them that I think are critical to make this space a success and are still largely unsolved technical problems. The first one is safety. I showed some methods that provide a strategy to be able to tackle introspection, simulation, measurement, but they're far from complete. And while they provide initial opportunities, ways to causally introspect these models and understand why they behave, to be able to prove to a level of acceptable risk the safety boundaries of them, and to be able to understand what they're uncertain about or don't know. All of these questions at the vast open world scale of embodied AI are yet unsolved. And then secondly, efficiency. If you think about what's going to bring this technology to the world, it's not going to be an expensive self-driving car that can only be manufactured at a very small scale. It's going to be something, as I said, that can be at smartphone or PC scale. I'm really inspired by so many products that have just driven innovation through efficiency. And I think being able to take AI from systems that are running on very large and expensive, powerful servers into something that can run on an edge device, something that can run in a low power setting, something that can run on a $50 computer. This is what's going to make this technology accessible everywhere. Efficiency cannot be underrated, and I think we've often seen through Wayve's history that efficiency can drive innovation, can drive impact, can drive scale. And so these are the two areas that I'd emphasize as interesting open research questions that if you're inspired by them, I'd love to continue the conversation. So wrapping things up, For me, it's been an absolute journey of a lifetime building Wayve, chasing so many frontiers, and I think we're just getting started. I think the future for embodied AI is going to be tremendous. It's going to be an opportunity for us to have machines that can really accelerate our lives in all kinds of different areas, give us time back, and allow us to delegate work that can open up so many new possibilities. Thank you so much for coming along tonight. It's been a pleasure to share these adventures with you, and I'm very happy to take any questions if anyone would like to ask any. Thanks.
Can I just say before we start, Alex, I want to thank you for absolutely inspirational and really, really very thought-provoking talk. I think people are going to be thinking and talking about this for some time to come. And for sharing all of this with you. Before we do take any questions, if you don't mind, I wanted to hand you this. So it's the 150th anniversary book telling you all about the department that you already know about. So thank you. Shall we take some questions?
Thank you.
Could you tell us, please, how your approach differs from that of Tesla, Waymo, Oxa, and others?
Of course. We've been from the very get-go building an end-to-end deep learning system, a system that learns to drive with data, and today is a transformer that goes all the way from sensor input to motion plan output. Now, as I mentioned, this was contrarian for so many years. I think in the last year, it's true that a lot of other self-driving companies have started to work on this approach. So Tesla last year publicly announced they're pivoting into an end-to-end learning approach. Waymo have more of a hybrid stack today that has some rules-based, more narrow AI systems, many different deep learning models that fit together into a wider architecture. I mean, I can't speak for their system, but at least what they publicly said, they have a system that brings together a hybrid approach like this. But in general, I think outside Wayve and Tesla, very few have pursued an end-to-end learning approach. Where we differ from Tesla and where we hope to offer a more scalable solution is a system that we hope to be adaptable and generalizable to many different fleets or manufacturers. We hope to see the system empower all kinds of different vehicles or fleets or other applications around the world in a much more open and generalizable manner. We now both are pursuing this end-to-end deep learning approach.
Who should we take? Should we take maybe Patrick first, and then there, and then there?
So can you talk a little bit about your the training schedule? I mean, how often do you retrain the models? Do you use all the data from everywhere into a single model? Can you talk about that?
I can, but it changes every week. We train dozens of models every week. We have a very efficient pipeline today for deploying our models on our fleet that's now running globally, and to test different hypotheses, to drive these vehicles into different scenarios. But of course, most of the measurement we try and do as much as we can offline through simulation. But the training regime today is, as I said, we're pursuing many different forms, and the latest recipe will change week on week as we push forward new ideas. Broadly speaking, it's a mixture of self-supervised pre-training at large scale. There's a lot of imitation learning on expert driving data and reinforcement learning on feedback or other learning signals that we have. So it's a whole mixture of learning signals. Essentially, is the more you can make it self-supervised, the more it scales. So self-supervision can be things like predicting the future, predicting what's going to happen next, can be predicting geometry, motion, or other signals that don't require human labeling. That's by far the most scalable, which is the predominant source of training.
Thank you. I think there was a chap here first, and then we'll move over to that
Hi,
side.
Alex. Thanks for a super lecture. It's David Sharp, ex-Ocado. Enjoyed collaborating with you. At Ocado, the big question, which still is outstanding, is when? So are you 90% there with only 90% to go? When do you think it will be actually self-driving in London?
Can you say?
Yeah, I've been quite careful not to publicly put out any timelines. Going back to the hype cycle, I I want to ensure that we don't overhype the space and cause any backlash or swinging back and forth around this. So we've been quite careful to, we of course internally have a very clear timeline that we're sprinting towards. I think what I can talk about the sequence of what's required to get there, and we can perhaps debate what the time constants might be. But so right now we're seeing some robotaxis operating in constrained environments in some cities around the world. The path to see those to grow to be ubiquitous is I think they've got to cost down by orders of magnitude, reduce their reliance on expensive sensors, enormous compute in the cars, and infrastructure that requires them to operate in a geofence. Typically, vehicle timelines and respinning into new vehicles can take 4 years. And we've probably got at least a couple of those. And so I think we've got some time and challenge for those systems to go to scale. The opportunity that we're pursuing that I presented today is one of seeing this technology deployed at scale in vehicles that are already manufactured in tens of millions of volume today, that have the necessary cameras, radars, and compute. And most of the high-end vehicles that are made today have that, and increasingly more the mass market ones. Now, the journey there is one, as I said, of scaling up from driver assistance to driverless. And that's one that I believe can be run as a data, as a learning loop, and these vehicles can be updated through over-the-air updates that increase those capabilities over time. The great thing is that path provides a very near-term path to global footprint, to global integration, and beyond. So that's why we're pursuing this path, because I think it's going to be the fastest path to scale. And so I'll let you infer the timelines.
Maybe one more, I think, just time-wise, because we have to get somewhere else after this. Okay.
Again, thank you for the talk. Very interesting and very inspiring. John Hill from Stract. You mentioned about multidisciplinary teams being the cause, cross-disciplinary teams. As you scale, how are you going to maintain that co-working across the globe and within your organization?
Yeah, I mean, I didn't even touch on today the journey that we've had from a couple of people in a house to now we're a team of about 450 people in a couple of offices all around the world. I think cohesion and alignment is one of the hardest problems through that. Some of the things that have really worked for us have been, firstly, keeping teams lean and keeping them focused, and that means outsourcing a lot of things that aren't core. Partnering, for example, we don't build our own compute, we partner with Microsoft on our cloud compute. On data collection, we partner with some of the largest fleets around the world. So firstly is keeping the team focused and highly leveraged. Secondly, frequently bringing the teams together in person has been something that has continually been so critical. And then change is the only constant thing, particularly around communication structures. The way that we empower decision making and ensure that we have high ownership in our team, people can move fast, but then bring together cohesion and cross dependencies. I could give you a framework that works well today, but again, in 6 months it'll be broken. And so we've found so many different frameworks to be really helpful throughout our growth journey. And actually, we just rolling out one in the last month or so that gives us a new sense of empowered roadmaps across all the different areas in our company. So those are some thoughts that come top of mind.
Thank you. I think just on the basis of time, I think we should draw this to a close, if that's all right. Thank you so much for coming and listening today and engaging, and Alex for giving us your time. It's been a real pleasure. Thank you very much, everybody.